Okay, today I would like to talk about qubits, as usual, and in particular how to represent them in something called cat notation, or better said, Dirac notation. I want to move on also to the so-called tensor product. The tensor product is basically a mathematical way of describing two or multiple qubits at the same time. And then finally, I would then talk about entanglement and give a brief introduction to entanglement. But let me start off by saying I am using a different mic setup for now, so the audio is a little bit worse. My apologies for that. Okay, so let's start with the basics. So before I mentioned what we could think of a qubit as living on the surface of a sphere. Let's make this mathematically precise, and we'll try to move away from sort of this geometric visualization for several reasons. First off, it becomes hard. This becomes really hard to visualize when you go to multiple qubits. The dimensions just grow too quickly. And will just also be more convenient to use the actual mathematical notation developed for this. And it turns out that quantum mechanics is really formulated in terms of linear algebra. And so there's sort of two important states. There's the so-called zero state, which are labeled in this way. I have this straight line here, and then this angular bracket here. And this is just shorthand notation for the following. So this is a two-dimensional vector where the first element is a 1 and the second one is a 0. Similarly, we have the 1 state, which is almost the same, except we have the 1 now in the second entry. And for convenience, these guys are called 0 and the 1, and they would correspond to, in this geometric picture, they would correspond to up, and the 1 would correspond to down. As I said, I want to, however, move away from this geometric picture, although I'll still appeal to it a couple of times because it will hopefully make more sense. But this idea of thinking of these directions in terms of vectors will turn out to be very useful. As a first remark that might confuse you, I mentioned that you could think of qubits on the surface of a sphere, right? And the sphere sort of lives, in some precise sense, in 3 dimensions. And you might now be confused by the fact that here, when I look at these guys here, they live sort of in a 2-dimensional space. Unfortunately, this I cannot really explain why this is. This would take a lot of... it's really not obvious to explain why this still works, but for now, let's just sort of ignore this fact and let's see what happens. Okay, so we have this up and this down state, and they are really vectors. They are really vectors in some complex vector space. So I can think of these entries here as really being complex numbers. So they live in some complex space, C2. Well, the 0 and this 1, they form a basis of this complex vector space. In particular, if I take any state, let's call such a state psi, I can always rewrite it as some coefficient alpha, 1, 0, and this was just a 0 state, plus beta 0, 1. This guy here, this psi, is really just an arbitrary state. I haven't specified anything, except that it has these parameters alpha and beta in front of the 0 and the 1. Okay, can these alpha and betas be anything? Well, they also have some interpretation, these numbers here. They're also called amplitudes in quantum mechanics, but coefficients also works just fine. And the question is, what do these amplitudes or coefficients represent? Well, now we chose a very specific basis here. We chose the basis 0, 1, and then we have these associated amplitudes in front of them. And if we fix the basis to be 0, 1, then these coefficients have a nice interpretation when we decide to do a measurement where we check are we in 0 or 1. Right, so I mentioned before that we could do these measurements where we could ask, for example, are you pointing up or down in this geometric picture? And in this case, the probability of seeing up is given by alpha squared. Well, I need to be careful. This alpha might be a complex number. I should also take the absolute value. Okay, so that's how we can interpret alpha. And we can do the same thing for beta. The probability of seeing, of observing down, given that we perform the measurement, are we pointing up or down, is here just beta squared. Okay, so these are probabilities, and these two occurrences, up or down, are the only two options. And so this imposes limitations on these alpha and betas. In particular, we want that alpha squared plus beta squared is 1. Right? This is also what we normally want from a probability distribution. When we sum up all the probabilities, they better add up to 1. And that's basically the same condition that we're seeing here. Okay, so now we sort of expressed our shape psi in terms of this nice basis, the 0, 1 basis. And then these coefficients have a nice interpretation. It turns out there's also another way of calculating or extracting these coefficients that will turn out to be more useful. So, first of all, actually, let me take a step back. Before we go and get into calculating probabilities for more general cases, let's rewrite this condition here. And this might be a little bit of a silly way of rewriting it. So I used this notation where I had this straight line and this angular bracket here. And this is called Dirac notation, and it has its uses. Namely, if psi is, for example, this number, alpha beta, then we can define its conjugate transpose, which we just sort of flip the angular bracket and the straight line. And then we say, well, this is the same thing as alpha beta, but we take the conjugate transpose. So we flip the vector and we make sure that we take the complex conjugate of the entries. So alpha conjugate, beta conjugate here. Why would we want to do this? Well, it turns out that this condition here is equivalent to the following. Let me write this out. So I'm going to write down this part here now. Well, this was alpha conjugate, beta conjugate. Now I'm going to write down this part, and that was just our ordinary vector. And if we write this out, we see that we get alpha conjugate times alpha plus beta conjugate times beta. But that is just exactly this previous condition that we had. And we want this to be equal to 1. Now, this notation here, we can also even shorten because we're lazy. Instead of writing down this middle line twice, what you'll see quite often in quantum is you just drop one of the lines. Okay, so this was already a first motivation for this Dirac notation. It expresses this idea of taking the conjugate transpose and just add some notation for that. So that just simplifies some writing that you have to do. and that will also make some calculations easier. Okay, so the thing, just to emphasize, the thing here on the left hand is really the same thing as the thing on the right hand, except that on the right hand we just used a shorter notation. Okay, great. This Dirac notation is also useful for more than just expressing this constraint here. In particular, when we perform a measurement where we ask, oh, are you pointing a certain direction given a certain state, we can also phrase it as follows. What's the probability that we observe some state phi given that we have psi? Oops, these are the same. So I have this state here, psi, and now I'm going to measure, oh, are you phi? This is one of the questions I'm going to ask. And it turns out that the probability is given by the following. So I take psi, the normal psi, then I take the conjugate transpose of phi, I calculate this whole thing, which will return just some number, some complex number in general, and then I take the absolute value squared. And that number gives me a probability. And so this is how we really calculate probabilities in quantum mechanics. We calculate these quantities here, and then square them. These quantities here are called inner products. And you may have seen that in linear algebra before. Okay, so maybe to reiterate, this Dirac notation gives us a convenient way to express the probability of observing a given state, phi here for example, given that we have psi. And it's expressed in terms of the inner product, and then since we end up with a complex number in general, we should also square it, take the absolute value square to get out a real number. And this is just the associated probability. Okay, so this shows us that sort of the general way of calculating probabilities. Let's go through some examples. Up to now it has been quite general, so let's look at some examples. Let's choose alpha equal to 1 over square root 2 and beta equal to 1 over square root 2. In other words, we have the following state. And when we write it down as a vector, we would just get this. This state is also called the plus state. And if you want to think about this geometrically, what this state is it's a state that is pointing right on this sphere. Let's check the constraint, whether we want to check whether this constraint is satisfied. So let's do that. Well, in this case, alpha is 1 over square root 2. So if we square that, we get a half. Same thing for the beta term. So this is just a half plus a half equals 1. So that definitely works. We could have also, instead of having a plus here, we could also have a minus sign. And this is also called the minus state. So these things here, just shorthand. We don't want to write down this whole thing the whole time, so we use the following shorthand here. And you can check that also here the constraint is satisfied of alpha and beta, that their absolute values square to 1 or sum to 1. Another state that I could have chosen is something like this. Which is almost exactly the same, except I have here now an I, an actual complex number. These also have some shorthand notation, but we won't go into that. I just wanted to highlight that really these coefficients can be complex numbers. Okay, so those were some examples of states. Let's now also perform measurements. Well, so let's say we have the 0 state. Right, this is the 0 state. And we're going to ask, we're going to perform measurement where we're going to check, are you in 1? Well, we go back again here. We look at this condition. And now let's calculate this. So the probability that we'll see 1 given 0 is given by the following quantity. Right, in the general case this was psi, and now we had phi here in the general case, but now we specialize to having 0 and 1 here. Well, you can check that if you write this out, let me use now square brackets, you get the following. And if you calculate this, you'll see you get out 0. And this is what we would expect. Our state is pointing up, right? It's the 0 state, and we're asking, are you pointing down? Then we get that this happens with 0 probability. Let's make it a bit more interesting. Let's say we're pointing down, but we now ask the question, okay, well, are you a plus state? Now, if you go through these calculations, you'll find the following. Oops, I should also square it here, I forgot. It's easy to forget. And if you calculate this, sorry, these brackets here should be absolute value squared. Let me update that. Absolute value squared. And then you can check, we get the following. It's just a half. And this is not too surprising. Again, when we think about the geometrical case, we have now an initial state of 1, so we're pointing down. And we're asking, okay, are you pointing to the right? Well, we saw already before, or I told you before, that this leads to a probability of a half when measuring. And that's exactly also what we get out here. One check that you can do for yourself is that if you measure, start with a minus state, and you ask, are you a plus state? You would get out 0. That's something that you should check. Okay. Let's move on. So when, let's see, yes. Okay. So we now have sort of the tools to describe a single qubit. Now let's move on to 2 qubits. And here things already get very interesting. Let's first consider the case where I give you 1 qubit first, which might be in some state psi 1. And then separately I give you another qubit that's in a state psi 2. Well, we would like to now describe in linear algebra terms this new state, right, having psi 1 and psi 2. And it turns out the way to do this is to use the so-called Kronecker product. We write that as follows. We use this notation here. It's a circle with a cross through it. And we can create a new vector out of this. It will now be a 4-dimensional vector. And you can think of it sort of as stacking psi 1 and psi 2 with each other. Let me explain. So if psi 1 is alpha 1, 0, plus beta 1, 1, and psi 2 is alpha 2, 0, plus beta 2, 1, Then the tensor product was given by the following. We first write down alpha 1 here, and then we write the whole of psi 2. Well, what of psi 2 in vector notation, it was alpha 2 beta 2. And now we do the same thing here, but with B1. Okay, why is the tensor product of this form? Turns out there's a good reason for this, but it's a bit hard to explain now in an introductory course. And so let's expand this. Now we'll expand this. We get here alpha 1 times alpha 2. That's really just this part here. Then we have alpha 1 beta 2, which is just this part here. And then the remaining entries are now B1 alpha 2, B1 beta 2. So this describes the state of two individual qubits, psi 1 and psi 2. Okay. So in general, a state will now be described by 4 parameters. So I have some psi, let's call it psi bar. This is now a 2-qubit state, and I can describe it as some coefficient alpha 3, 0, 0. That corresponds to this entry here, plus beta 3, which corresponds to this entry here, plus gamma 3, 1, 0, and finally plus delta 3, 1, 1. I forgot to introduce some notation. When I write something like 0, 0, it's really just shorthand for 0, tensor 0. But I don't want to write down this the whole time. So that's why I just write down this thing here on the left. Okay, so now our 2-qubit state requires 4 complex parameters to be described. And again, as before, we have the similar condition that psi bar, the inner product with itself, should equal 1, which again, in other words, is just that alpha 3 absolute value squared plus beta 3 absolute value squared plus gamma 3 absolute value gamma squared plus delta absolute value squared equals 1. So these 4 parameters describe a general 2-qubit state. Now this is where things get interesting. If you look at these parameters here, the alpha 1, alpha 2, and the rest here, they don't allow you to write down the most general 2-qubit state. What do I mean by that? Well, let me give an example. Let's say I give you the following state. Now psi bar is given by 1 over square root 2, 0, 0. So alpha 3 is equal to 1 over square root 2. And now the next 2 terms are 0. And then we have that the term from the 1, 1 is also 1 over square root 2. Well, this is most definitely a state in a sense that when we take the absolute value squared of this guy, sum it with the absolute value squared of this guy, we get a 1. So it satisfies this constraint that we see here up above, right? But it is not of the form of anything like this. So we cannot write this state here as the tensor product of two individual qubits. Okay, why is that? Well, if I write down the vector of this guy here, it looks as follows. Let me clean this up. And now, let's check what would happen if this were indeed of this form here. Well, we're going to go above and look at this expression we have here. Let's move this down a little bit. Okay, well, we see that the second entry is 0. So that would require that either alpha 1 is 0 or beta 2 is 0. It cannot be the case that alpha 1 and beta 2 are non-zero and that the product is 0. That is impossible. So let's assume that alpha 1 is 0. Well, if alpha 1 is 0, then this term here should also be 0. Right? Because we have a 0 number, we have 0 multiplied with some other number, well, that should always equal 0. But this number here is definitely non-zero. Okay, so let's write that down. We have that alpha 1 or beta 2 is 0. We saw that if alpha 1 is 0, then we need to have that 0 times alpha squared is 1 over square root 2. That's basically what it says here. These two guys should be equal to each other. But that's not possible, so then let's look at the other case. Well, then maybe beta 2 is 0. But then we run into the same thing. Now we see here, hey, we multiply here with some number with a 0 number, beta 2. So this last entry should be 0, but we see here that this entry here is non-zero. So we get in both cases, should be 1, this should be 2. We run into a contradiction. Right, this is a contradiction, and this is a contradiction. So what does this mean? Well, it tells us that our state, psi bar, really cannot be written as a tensor product of two individual qubits. This is really the mathematical definition of entanglement. The state is entangled. Psi bar is entangled. If I cannot write it, it's impossible to write it as a tensor product of two individual states. Oops, not equal. And important here, I should consider I'm allowed to choose any two qubit states. So maybe as an example, if I take the following state, then you might think naively, oh, this looks sort of entangled, like I have, entries everywhere. But actually, if you look closely, you can check that this is the tensor product of the plus state with itself. So this state is definitely not entangled. You should also check, by the way, that minus tensor minus is the same as the guy on the left, except I have some extra minus signs. Okay, I gave you now the definition of what entanglement is, but how should we think about this? Well, entanglement is really this weird correlation between two different states or two different qubits. And we have entanglement when we sort of cannot describe a state in terms of its individual components. So if a state can be written like this, I can really sensibly talk about qubit 1, that's just a thing living here, and qubit 2 living here. They're sort of independent. But now if I have a state that's not of this form, then it doesn't really even make sense. I mean, it's hard, one cannot reason properly about the state of an individual qubit, because the state of the two qubits is really shared amongst the two. Of course, this is very hand-wavy, and we can only make this really precise with mathematics, but that's sort of what's happening. Okay, let's have a look again at the state. So we had the state psi bar, which was given by the following. And this guy has a very important state. It's called a Bell pair or a maximally entangled state. It's very important both in applications but also from a foundational point of view. Let's try to understand a little bit what's happening. Right, I told you the state is entangled, but can we maybe get some clear sense of why we would call it entangled? Well, I mentioned before that in quantum mechanics, really the only thing that we can observe are measurement statistics. We cannot directly look at our states, we can only perform measurements on them, and then decide, sort of glean information from the state. So let's say we have a state like this, and it's on two parties. So the state is held between Alice and Bob, and we say that Alice and Bob are now entangled. So they have two qubits, each of them has one qubit, and they're both entangled with one another. And now let's try to understand what happens when Alice and Bob perform local measurements. Okay, well, let's say that Alice and Bob decide to measure in they decide to measure whether they have 0 or 1. If you think of this geometrically, we think whether they're asking, are we pointing up or down to their qubits. So if we compute now then the following, right, we use the same rule that I described before. Let's look at what's the probability that they get 0, 0. So that's this quantity here. Well, if we write this out, we see that 0, 0 is given by 1, 0, 0, 0. Here we have 1 over square root 2, 0, 0, 1 over square root 2. Need to take the absolute value squared. And you can check that this is equal to a half. Okay, so when they perform the measurement associated to this, they would say, okay, well, with probability half, we get out 0, 0. Okay, well, what happens if we do 1, 1 instead? Well, you can check that this also gives you a half. And note that half and a half, well, they sum to 1. So if we were to look at, for example, the probability of observing 0, 1, psi bar, we should get out 0. And you should check this yourself. And this turns out to be indeed the case. So what does this tell us? Well, it tells us that when Alice and Bob both decide to measure are you pointing up or down, they will always get correlated outcomes. If Alice sees a 0, then Bob will also see a 0. The probability that they'll see this specific outcome will be a half, but they always know they're correlated, right? The probability of seeing 0 on Alice's side and 1 on Bob's side, that never happens. That has probability 0, as we see here. Okay, so they have this sort of shared randomness, but it's correlated. So they don't know what outcome they're going to get, but they know that they will be correlated. So if you read like popular science articles, they'll quite often say like, oh, this is very peculiar, right? This is what entanglement is. But I would very strongly disagree. Because let's say we have the following scenario, right? We have here Alice and Bob. And they agreed with another party, let's call it R for referee, that the referee will either prepare 0-0 state and send one half of it to Alice and Bob, or the 1-1 state and send one half to Alice and Bob. And the referee won't tell Alice or Bob which state they're going to send, just that they choose this completely random. So maybe Alice has 0 at a certain point and Bob has 0. If Bob now decides to measure whether it's up or down, he'll say, oh, I'm pointing up. But he knows that the referee was either sending only 0-0 to Alice or 1-1. So after measuring Bob's state, Bob will know, hey, Alice has a 0. Well, this is not too surprising, right? Like, we agreed beforehand on what we would do, and now we just choose a random outcome, a random state to send here. The referee decides on this randomly. This is not too special, right? This is also something we can do classically. Instead of the referee preparing these states, he may as well just prepared, took a piece of paper and wrote down 0-0 and sent this to Alice and Bob, or 1-1 with the remaining probability. So there's nothing quantum happening there. This idea of being correlated, that's nothing special. What is special is that Alice and Bob have quantum states. So unlike a piece of paper, they can decide to measure it along a different axis. They can perform different measurements. And it turns out that it's important now, the correlations they have in those, when they perform these different measurements. Let's look at an explicit example. Let's go to this case here again. And instead of Bob measuring in the 0-1, let's say he measures whether he has plus or minus. Well, you can check that his outcomes will then be completely random. That follows from the fact that this holds. Sorry. Oops, let me rewrite this. So we have the state 0, and now we want the probability to know whether we're in a plus state. It's given by this quantity. And this is equal to this quantity, the probability of observing minus, which is just a half. But if Bob performs this measurement, he learns absolutely nothing about Alice's state. Because he cannot distinguish whether he had a 0 or a 1, and so he also doesn't know whether Alice had a 0 or a 1. Now, this gets more interesting when we have entanglement. Because one thing that you can check is that if I take this psi bar state, this entangled state here, I can now also ask, okay, well, what's the probability that Alice and Bob will measure plus? And I advise you to go through this calculation, but what you'll find is that this is equal to a half, which again in turn is equal to asking whether Alice and Bob have minus states. And so we see again here that Alice and Bob are correlated. If they decide to measure in this plus-minus direction, they'll either both get pluses or they'll both get minuses. And so these correlations, they persist even when you decide to measure different, if you decide to perform different measurements. And this is really where the power of entanglement comes from. It's not the idea that we have correlations, that we already have in the classical case, but these correlations can now sort of persist when we decide to do different measurements, and that's not possible classically. I would like to close maybe with actually giving a name to this rule here. So We had this rule here, right? This allows us to calculate probabilities of observing certain states, given that we have a certain state psi. And this is called the Born rule. And this is really a fundamental, or Born's rule, I guess. It's really a fundamental postulate of quantum mechanics. And it's really important to understand this and to be able to do calculations with this. Again, for the sole fact that the only thing we can really calculate in quantum mechanics are measurement statistics. Or the only thing that we can calculate and observe are these measurement statistics. So, and Born's rule tells us exactly how to do that. Okay, so I give a quick introduction to single qubit states, how to write them down as vectors, how to interpret these coefficients that they have. Then I discussed the tensor product, which allows you to extend to multiple qubits. And then we saw that there's examples of states that cannot be written as the tensor product of two individual qubits. Well, we say that those states that cannot be written in such a way are entangled. And then we had a look at what kind of effects this could have when we perform measurements on the qubits individually. And we saw that we could have these interesting correlations that we don't have in the classical case. And it's really sort of this feature that describes entanglement. In the next lecture or next video, I want to talk more about measurements and these statistics. And I want to talk more about this maximally entangled state, because it has also some interesting properties that we can use to sort of prove things about teleportation. So hopefully in the next video, I get to talk about teleportation.